much. Good afternoon. So today I want to talk about some of the tools that I use in solving problems. And there are kind of two kinds of problems that I'm going to talk about solving, or at least trying to diagnose on the way to solving. The solving part's usually the hard part, but we like to figure out exactly what's going on. And so the kind of tools I use for this, the first category I would put as performance analysis. And so those are tools that are maybe giving us some kind of information about latency or operations per second or bytes per second, that kind of thing. And the second kind of category is what I sort of call behavior analysis, and that's more looking at exactly what a program is doing, what steps is it taking, maybe trying to figure out, rather than it being too slow, maybe it's doing the complete wrong thing. And in my day-to-day role, I've been some kind of systems administrator or SRE for more than 15 years, but currently I work in the Ubuntu support team, and we support a wide array of customer problems. So it's not just one product, it could be anything that runs on Ubuntu. I spend quite a bit of time on OpenStack and Ceph, which themselves have lots and lots of components, but really someone could open a case about anything. And so we don't always have built in the best tools or best metrics for finding out what we want to know, because the problems are kind of always different. And I need to do this at runtime and in production, and not crash or slow down the system in the process. So that's kind of what we're going to talk a bit about today. And my hope is that I'll introduce this new tool that you may be either a little bit familiar with, or maybe give you some ideas about what you can do with it to maybe help solve your problems. So in the performance analysis kind of bucket, we have some traditional tools that you might be familiar with. These are things like IOstat or top, VMstat, NFSstat, BWNG, all these kinds of tools. And what most of these tools are doing is they're very fast. They don't typically impact our system performance because they're looking at some kind of performance counter that usually the kernel is already kind of taking care of and counting for us. How many transactions are going through a network card or a disk or something to do with a process. These are super great for a top-down view, but some of the limitations, number one, is they really make heavy use of averages, and averages are really good at hiding outliers. And we'll talk in a minute about why that can be a problem. And they often have a predefined and limited kind of breakdown. So often we might be able to see disk statistics for a disk, but without correlation to a process. Or we may even be able to see I/O information for a process, but without correlation to which disk that I/O information is from. Another kind of subcategory of these tools, and top and netstat are really good examples of this, is they'll take an instant snapshot of the system every second, and if something happened in like 0.1 of a second in between the last snapshot and this snapshot, it might miss that completely. So in the case of top, if you're launching lots and lots of processes that take a very short time to execute, those may not show up in top at all, and you might miss the CPU usage from those. And netstat will show you all the live TCP and UDP connections on a system, but only at the instant you run the tool. And you won't see all the ones that were short-lived in between those executions. So I'll look at some examples of where averages can hurt us. So this is a tool that I really like to use called IOstat, and it gives us a breakdown of I/O performance statistics for each disk on the system. And so here we can see we've got multiple disks, some hard drives, an NVMe device, and some columns of data. So we're seeing reads per second and writes per second. That's IOPS. The read kilobytes and write kilobytes a second. That's the bandwidth going to the disk. And also the average latency. So the RA wait and the write A wait is the average latency of those operations. This is kind of good as an overall, but this average latency, and latency can be a really important thing to look at, is an average over all 27,000 of these operations that happened in that second. And so it could be that all 27,000 of those took 0.03 of a second. It could also be that almost all of them except for one took 0.01 of a second, and one of them took 3 seconds. And if you've got a disk I/O operation that's taking 3 seconds, that's really interesting, but you can entirely miss that in tools like this. If you've been around I/O or storage, you might understand this, but if this is confusing, I think one that we can all relate to as any kind of computer enthusiast is CPU usage. And so in this example of top output, I'm running the FIO benchmark tool, and I've set it to only use one thread to kind of stress a point in this case. But we can see top is telling us that our CPU usage is like only 6%, and 93% of our CPU is idle. But at the same time, it's telling us that FIO is using 100% of our CPU. And these numbers kind of don't add up. And if you haven't used this tool before, it might surprise you. The percentage of CPU, it doesn't go to 100, it actually goes to however many CPUs you have times 100. So if this was using my whole system, it would say 3200%. But we can ask top to break it down. So if you hit the number 1 key on top, it will actually show us all the CPUs on the system and the utilization of each one. And in this view, we can see that actually one CPU is running it at full steam, because FIO is single-threaded, it can only run on a single CPU, but the other 7 CPUs are idle. And so if we only looked at that average we had here at 6%, 93% idle, we might think our CPU is not a problem, when in reality, one CPU is a problem, and there is a bottleneck that we were missing with that average. And these are more simple ones, but these kind of problems show up everywhere. In any kind of latency or utilization of any kind of system resource, these outliers and averages hide stuff from us all the time that end up making it difficult to solve problems that I hit quite often. Another category of tools, which is my behavior analysis kind of category, these tools, rather than looking at very fast performance counters, are trying to look at everything a program is doing. strace is probably my favorite, and strace will attach to every system call a program makes and report exactly what that system call was, how much data was written, it can even tell you what data was written. But this tool transfers every one of those operations from the other process into user space for strace to then print out, and that's very heavyweight. If you're doing a very small program, that might be a small amount of data, but if you're trying to analyze something doing gigabits a second or gigabytes a second of disk or network, number one, it won't be able to keep up with processing that amount of data, but it'll also slow down that application. Block trace is a pretty awesome tool. It's kind of a kernel facility. It'll dump out every block operation that happens on the whole system, every request queued, when it comes out of the queue, when it goes to the disk, when it comes back. But again, it's going to queue all of that information out into user space and into a file, and that's very heavyweight. iptraf looks quite innocent. If you run iptraf, the first mode will tell you every connection and the number of bytes that are coming through all those connections. But to do that, it's actually packet dumping the entire network card into iptraf to find all those values. At a few megabits, not a problem. If you're doing 10 or 20 gigabits a second, that can be a problem. And even just debug logging, if you've ever turned up a debug in something to level 1, 5, or 20, the amount of stuff coming out usually will slow it down. So those are the kinds of problems we have with these behavioral analysis tools, but often they can tell us things that those performance counters can't, because there's only so many of those performance counters, and if one of those doesn't cover the situation we're looking for, if we kind of look at this detailed output, we might be able to find what we're looking for at a cost of a big slowdown. To demonstrate how big that slowdown is, I've got here an example case of running DD, and that's just a disk copying tool we probably all use with at least a Raspberry Pi or something. I'm reading from dev0, which is a string of null bytes, and I'm writing it to dev null. So I'm reading a bunch of zeros and throwing them away straight away. To make the example a little contrived and stand out, I'm doing that 1 byte at a time. I'm not batching it into 4 kilobytes or a megabyte, and we're going to do it 500,000 times. And so if I do that just with DD on its own, it takes 0.2 of a second, which is pretty fast. If I use strace, and I don't even ask strace, I ask it with except. I say, I only want to look at the accept system call. That's to accept a connection for the network. And DD doesn't even make network connections. If I ask it to do that, that same task will now take 18 seconds. That's nearly 100 times slowdown. In a production system that's very busy, that's a penalty we may not be able to incur. On a development or test system, it might be reasonable, or on a quiet system, I've used it a lot, but there are cases that's not going to work for us. And the reason why it's 100 times slower is because the way strace works, it uses a function called, in the kernel called ptrace, which is the debugger interface. It's the same interface GDB uses, and it's remote controlling DD. It's literally like a remote control. It says to the kernel, right, ptrace syscall, I want you to run this program until the next system call. The kernel says, okay, it runs, and it does a right system call, and then it goes into the kernel to do that system call, and it goes, oh, I've got to talk to strace. It wanted to know. So it's paused DD. DD is doing nothing. We go to strace. It goes, cool, we had a system call. I want to know what the system call was. To find that out, it needs to know the CPU registers in the context of DD. So it asks the kernel what were the registers. It goes back to the kernel. Kernel sends it back to ptrace. Ptrace says, great. Now we need to actually run the system call. So it goes back to the kernel. It actually finishes the work of that right system call. But then we go back to strace again. Why do we do that? Well, at the start, we had the registers were telling us the parameters to the system call. So I want to write this data to this file with this many bytes, but we didn't know the result yet. And so after it runs, we have to then get the registers to get the result. But at that point, we can no longer see all the parameters that were passed in, so we have to interrupt it twice, once at the start, once at the end. So it gets those registers, then it goes back to the kernel, gets those registers, then says to the kernel, okay, you can continue, send the data back to the process. And so that's context switched from DD back to strace through the kernel 8 times. And that's why it's 100 times slower. And DD has to wait in all the time here we've spent in strace land, DD is doing nothing, and so that's why it's slowed down. So it would be really great if we could write a custom tool to gather performance metrics on anything we wanted. It would be also super great if we could group those in some way we wanted that wasn't predetermined. Might want to group those by device, network card or disk, by which process, by which C group, anything we can kind of think of. And it would be awesome if we could do that, or even just get the same information we had before, but with a much smaller impact on system performance. And the good news is we can do that, and there are a number of ways we can do that now. So here are a few quick demos. So these are bpftrace tools, and I'll explain how they work in a minute, but they can do some really interesting things. So here's one called get host latency, and it will actually trace not just one process. strace only attaches to one process at a time. We can actually trace the entire system with every process, and we're going to hook into the get host by name system call in libc and say every time that happens, I want to collect that and then print out which process was looking at which host name and how long it took. And that latency is kind of one of the cool things we can get from bpftrace that other tools often won't show us, a per request latency. And I've solved real problems like this when I was doing web hosting before now. Your custom applications would be written in WordPress, and the wonderful thing about WordPress is there's like 100 million plugins written by 100 million people who kind of know how to write plugins, and then people install like 100 of them. And so you get all these bad decisions 100 times amplified, and often these are written by people maybe that live in the US, and they have a like maybe 20 millisecond or 30 millisecond latency to the entire internet. Most of us in Australia would know that our latency is 10 times that, like 300 milliseconds for most things. And so if you make like 20 network calls or 20 DNS calls at 0.3 of a second each, that really adds up, and suddenly it takes 10 seconds to load your web page. And so this is an example of a tool we can see, well, how many of those requests did we make and how long did they take? Another tool that we have, and these are all kind of in the bpftrace toolkit that we can do custom ones, is UDP Life, and it will show us all the connections, not just TCP, but UDP connections that happened on the system and how long they took, how long was traffic going back and forward. In this case, it's kind of a more generic version of the last one, and the last one we're looking at only DNS requests. Now we're kind of looking at latency by program of all UDP connections and how long they took and where they were going. And so in this case, we can actually see the DNS, same DNS requests and their latency. The latency is here in the millisecond column, and port 53 is DNS. But we can also see an NTP request here that had a 15 millisecond latency. And unlike netstat, this is going to show every connection in real time as they happen. And again, for the entire system. Another tool is OpenSnoop. It's going to show us every program, what paths they opened, and whether there was an error for that. And so far, those kind of 3 tools I've shown are in the category still where they're transferring a lot of data to user space. It's kind of every operation. One of the other nice things we can do with bpftrace is we can start to summarize information. So instead of transferring out of the kernel into the user space analysis tool every operation, we can send only a summary. And here's an example of that. We're looking at the I/O latency of every I/O request to a disk on the entire system for every process, but rather than just an average, we're now bucketing it with a histogram. And so in this example, the vast majority, 8,000 operations, took 8 to 16 microseconds, another 8,000 took 16 to 32. And you can see this is kind of like a bar graph of like what proportion of the total requests were in that bucket. Most of them are very fast, a few tens of microseconds. For some reason, we had one request out of 30,000 plus requests that took 1 million microseconds. That's 1 to 2 seconds. And these are those outliers I was talking about. If you had one program made all of these requests sequentially, it doesn't matter that every single one except for one took like 10 microseconds. One of them took 1 second, so that entire process is going to take a second to complete. And those are the outliers that we need to understand when we're trying to solve some of these weird problems. So what's unique here is that we're getting a histogram, not just an average. Here's another kind of tool that's doing some summary and analysis called syscount. And it's just showing the top system calls by ID. This tool unfortunately doesn't print the friendly text name, but it is possible to do that. And also the top 10 processes by process name, so which processes will make in the most system calls. And we can customize all of these things. These are just example programs. Whatever problem you're trying to solve, you can change that summary or analysis to be what you want it to be. So what makes this possible? So that's a little taster about what we can do with this tool. Well, let's understand how it's doing it. So the first technology it's making use of, it comes from the ftrace subsystem, which was merged way back in 2008. So it's really not that new of a technology. And the kind of first part that kind of ftrace brought in was this ability to have these events in the kernel that we could attach to or record in some way. And there are a few different types of those. There are more I'll explain in a minute, but a couple of the main ones. The first are these static trace points, and they're kind of like the kernel developer of that disk subsystem or net subsystem has defined some trace points that aren't going to change, along with some predetermined information that's going to record about them. It might be the network device name, it might be the file name, that kind of thing. And those are ABI stable, so we can rely on the kernel. Even if the internals of the kernel change, that trace point is always going to have the same name and output the same information. We also have the ability to attach onto any function in the kernel. If you go looking through the kernel source and there's something that interests you, you can attach to any one of those functions, and we can also trace those. But in those cases, on different kernel versions, those functions might change, and then you also have to figure out how to get that extra context yourself. If you want the file name or the disk or something like that, you have to start poking around in the data structures. That's great when you get kind of really good at it, but for the more typical case, it's nice to have these predefined trace points that know already kind of what information to get. This infrastructure is also super high performance, and the way that works is when the kernel's compiled, and there's a couple of different mechanisms, different places, but basically it puts out a string of NOP, no-op opcodes for the CPU to execute, and CPUs are really fast at doing nothing. That's been optimized to death by the CPU vendors, and so there's just like these 5 bytes in memory that do nothing, and only when we turn on tracing for a certain kind of function does that in memory get overwritten with instructions to actually jump out to the code to handle this performance analysis. And so every function in the kernel is ready to be kind of traced like this, but there's no performance impact until you turn it on. This incidentally is similar to how live patching also works. It'll actually patch the start of the function to like go off to the new version with live patch rather than the existing one. They're kind of related. The second technology that kind of brings this together and makes it really work was we moved, in the strace case, it was like a remote control for the process, and the kernel would send control to strace, and it would tell the kernel like what it wanted to do back and forwards, back and forwards. Now with the ftrace system, we have this ring buffer in memory in the kernel, and the kernel itself handles the trace event, so it doesn't break out to that user space analysis application at all, and it writes that trace event into a ring buffer in memory, all in kernel context. And then the user space tool reads out from that buffer asynchronously at the same time. There's no lock between them. And what that allows is now our recording is entirely in kernel space, so we're not wasting all that time context switching back and forwards. And our process isn't paused either. That little bit of recording work, it's just like poking a few bits in memory. That's very fast to do compared to all that jumping back and forwards. One of the disadvantages of that, however, is if we have those predefined static trace points, the kernel knows how to get that context and it knows how to put it into that buffer in memory so the user space application can read it. If we don't have a predefined trace point, and this happens, we want to just trace a random kernel function instead which doesn't know how to get its context, then the only thing we can record is that that function was called, and we can't really store the context about the disk or the length of the operation and that kind of thing. This has some safety elements built in as well. If the buffer fills up, those events just get lost. And so rather than the kernel stalling and maybe making the application slow if for some reason the user space side can't read fast enough, it just drops those events. And if the actual processing of these events take too much time, the kernel also has mechanisms for throttling that time back to make sure that it maybe is a few percent of your system time at most. And so if we look at the effect of this, so here's, before we showed that same DD operation, it took 0.2 of a second. If we straced it and didn't even do any work strace was interested in, it now took 18 seconds. Well, if we use perf trace instead, which takes advantage of that kernel infrastructure to trace the event, and also uses that ring buffer so that the applications are not waiting on each other. Now we can trace the same information in 3 seconds. That's still 15 times slower than our baseline, but that's a huge improvement over 18 seconds. And we can improve that again if this was tracing every system call, reads, writes, connects, everything. If we narrow that down again to only the write system call, and remember here it's taking us 18 seconds to observe nothing. Here we can observe half of the work the entire process did, because it's reading 500,000 bytes and writing 500,000 bytes, so half the work is reading it, half the work is writing it. If we only look at the writing of it, we can now get that down to 1 second. That's only 5 times slower than our baseline case. But we're still copying a lot of data to user space. So every one of those operations is going to this ring buffer, and user space is reading out all 500,000 of those operations. So we're way faster, but we're still wasting resources that maybe could still be improved. And so that's where BPF comes in. And so the origins of BPF were in packet capture. So when you ran TCP dump and you were filtering on port 22, without BPF, every single packet would have to be sent in the same way we've just been discussing, sent out of the kernel into TCP dump. It would then parse the packet and only print it if it matched. And at gigabits a second, that's going to be a problem. And so the BPF was this little virtual machine that was put into the kernel where we could define a tiny little program and send it to the kernel for how to filter the packets. And so now the kernel would take a program that TCP dump wrote. It would verify that that was safe, it wasn't going to corrupt memory, it wasn't going to take too long to run. It has all these safety checks that make it safe to actually put user code into the kernel, which sounds a little crazy, and uses that to filter the packets. And so now, only the packets we're interested in are actually sent out to TCP dump, which had a huge performance win, but it was very specific to packet capture. And this was in 1992, so a very long time ago. In about 2013, some developers took that BPF and they enhanced it. They added that little virtual machine, they've added more registers, more storage space. They made it JIT compiled, so rather than kind of interpreting that virtual machine, it's now converted to machine code, kind of like JavaScript might do. And they added the ability to drive these programs not just from packets, but from all sorts of different event sources. And one of those event sources is these same events that we're tracing. So those static trace points, those kprobes, all these event sources can now be connected to a BPF program. And we have all that same safety. The kernel is going to verify it. It actually reads and parses and understands the entire program before it loads it to make sure it won't crash, that it won't take too long to run, that it can't access unsafe memory and that kind of thing. That does put some limits on the program, and so to get a lot of the work done we need to do, the kernel has little helper programs. The BPF program can basically make some function calls out to certain kernel programs that will maybe make sure that whatever you're getting back is safe. The win this gives us is now we can take any tracing event, and instead of just putting the full output of that into the ring buffer and sending it to user space, now we can process that in kernel, and we can actually use code just like the packet dump to summarize or extract data in the kernel and then put the result of that in the ring buffer that's sent out to user space. And now we're only transmitting a very small amount of data out to user space, and so we're even faster again. And so if we look here, I've written a tool in bpftrace using this technology to do the same thing we did here. So before, it took us 1 second to trace every write call because we were transferring every write call out to user space. But I might have just wanted to know how many there were. And so I wrote a program which counted how many write calls there were, but it counted all of that in the kernel, and the only thing it sent to user space was the number 512,000. And now that takes 0.3 of a second, which is only 50% slower than our baseline case. And this is a really contrived example because we're doing a purely system call kind of load work. If in reality this program spent a lot of CPU time doing actual kind of work programs do and not just sending data back and forwards, that performance impact would be even less, often maybe 5 or 10% at most. And so as an example of that, if I use FIO, this is a really good disk benchmarking tool with an actual kind of benchmark. I can do 34,000 IOPS a second with no analysis running, and if I turn on a tool to analyze the latency of every operation on the system, sorry, I get 37,000 without it, but it only drops to 34,000 when I start analyzing the latency of every request in the system. So that's a much, much smaller drop than we have with all those other methods. Incidentally, BPF was first added to the kernel, eBPF was first added to the kernel for strace, well, not just for strace, but for a thing called setcomp BBF. And so this was a little program we sent to the kernel, and when we used that ptrace mechanism and said intercept every system call, we could send a little program to the kernel to filter out which system calls we wanted to trace. And so it wouldn't actually wake up strace for all the unrelated system calls, only the ones we wanted. And this is used for a few things, but when we use it in strace, we can halve the amount of time we take, but it still takes 10 seconds, versus the 1 or 0.3 of a second that we've managed to take using this in-kernel collection of the data and in-kernel analysis. Because this is only just cutting out all the events we didn't care about. It still transfers all the events we care about to user space with strace. So let's have a quick look at the language of bpftrace. The nice thing about bpftrace is you can actually write bpf programs in Python or in C or in Go, but doing that is quite verbose, and if you're a software engineer, that's quite possible. But as more of a sysadmin or SRE type person who's maybe knows enough to be dangerous when it comes to coding or how the kernel works, that's quite a forbidding kind of task. bpftrace is a much nicer custom language that lets us write these programs in a much more friendly way. So here's an example of what the language looks like. Sorry? Yes, so the bpftrace language is inspired by the dtrace language, which was a tool on Solaris from 2005, which did very much the same thing in the same way. It was inspired by awk. So the reason it looks like awk is because it was heavily inspired by awk. And so that's why we have a begin and an end, so we can run some code at the start and end of our script. In this case, we just print out a nice little string so the person knows we're actually doing something and we've started our work. We can specify a probe type, and so an example of a probe we might do is a system call write, but there's a lot of different probes, and we'll look at all of them in a second. We then have a predicate, so we can actually have a condition, again, like awk, we can say, I only want to match on this probe if the process is a Python process. And then we can run some actual code. And so in this case, we're going to store a global array called start. We're going to index it by the thread ID, and we're going to store the system time when that probe was called. Here's an example of another probe. We've got a kind of more complicated predicate. First, we're going to check that we actually had a non-error return value. We're also going to check that we're Python, and we're going to check that initially we kind of match this other probe first. We'll make sure we match that first, and then we'll do some other logic. And in this case, we're summing the latency, the time it took from the first function to the second function. And so we calculate that latency. We sum up that latency per process ID. So for whatever we're probing, we're going to add up the total time spent in that time period. And then every 30 seconds, we're going to print out all that data we've stored. And at the end, we'll print it. And so that, a bit like a lot of IOStat and top and stuff do, it can print out kind of like intervals and then kind of print out the result at the end.
There seem to be some magic variables in there, like count.
So the question is, there seems to be some magic variables like count. So yes, so there are a bunch of, it's actually not a variable, it's kind of a function, but it basically just says count up that, you're saying I've actually made a mistake when I was making the slide. I see what you're saying, my mistake. I did at count. That should probably be at time. That was just an error in my slide preparation. So yeah, that should just be at time. This is not a real program. I was kind of just trying to show the syntax, but thank you for catching that. And so here are a bunch of one-liner examples of BPF programs that actually do things. These come straight from the bpftrace manual. And so here's an example that we're going to check all the files opened by a process. So we get the open system call, and we want to print out the file name and com, which is a special variable bpftrace knows it's just the process name. We can count system calls by program. So we match this probe, and we're just going to count indexed on whatever the program name is. So even if you have multiple copies of Python running, all of them are going to kind of count together. This is a case of we're summing, so rather than just counting, we might want to sum the number of bytes that are being read. That's an example of that. Here's our histogram we talked about. That's how you would create a histogram. All these kind of different things that we can put together. We can do printf, we can do multi-dimensional arrays, all sorts of stuff. I mentioned before there are a bunch of these different probe events we can attach to, and so the two we talked about so far, one was trace point. These are these predefined ones in the kernel that they've kind of given us as a convenience, and it already knows how to extract some context. We can also do a kprobe, and that attaches to any kernel function. And the kprobe has a kprobe and a kretprobe. So as I described earlier in the strace example, at the start of a function, we need to intercept it then to capture the arguments to the function, and then we need to intercept it at the end to get the return value, or perhaps collect the results of that function running. So we kind of probe those separately. We can also probe user space programs. So a uprobe will actually probe a function not in the kernel, but in a program or in a shared library. And as I'll show in a bit, for example, we can probe the SSL library on every process in the system and kind of capture information from that. User space programs can also, much like trace points in the kernel, there are statically defined user space trace points called USDT. A bunch of bits of software have some of those. And we can also do a bunch of periodical things. We can do things on an interval. We can do things based on performance counters from the CPU. Those ones get a little bit more advanced. I'm not going to talk about those today, but there's a whole range of them that you can look at. The user space probes, the kernel probes, and the trace points are kind of the most interesting ones. So I promised 5 recipes, so I'm going to go through and talk about kind of 5 solutions I've actually used when solving problems, and kind of show the program and what that looks like. The first one is I was trying to profile some Python applications. Now, bpftrace actually has the ability to get the kernel stack and the user space stack, the actual call stack like a debugger would, but it can only do that from programs with like traditional like frame pointers and debug info. That doesn't work with Python right now. That might get fixed because there's some ability to add like some magic so that it can kind of understand from Python what's going on. But I was using a different Python tool called Austin, which will profile the Python application. But I wasn't launching Python, something else was. And so what I wanted to do was capture every time Python was started and then immediately launch the Austin profiler to profile that Python process. And so this is a simple program where we're going to capture every time we execute something. The system called execve. If it was successful, and if we're a Python 3 process, then we're going to output the process ID, and then I process that to launch the process. I was using this because I wanted to profile, at Canonical we deploy software with a bunch of Python code basically that's orchestrated by a tool called Juju, and it was launching them, and so I just wanted to profile everything it launched without having to modify Juju, so that was a super easy way to do that. Here's another example. A version of this tool ships with bpftrace, but it doesn't tell you the offset into the disk that it was reading from and the link that it was reading. So I was debugging a Ceph case, and I wanted to understand where from the disk we were reading it and at what length and then what the latency was. And so I customized that tool and enhanced it to understand the disk offset and understand the disk length and kind of output that. In doing so, I discovered that the reason trace points are great is because kernel developers who know much more about that kernel subsystem have predefined all that information and how to get it. I was using kprobe, so I had to look through the data structures and follow several structures myself to find things like the length and the offset. And it turns out I did that wrong in such a way that the length and offset looked right most of the time, but sometimes it was wrong entirely. And so I do advise some caution if you're a kernel developer that knows enough to be dangerous, that's me, to maybe verify the output of things you've come up with if it's a kprobe, or rely on someone that maybe knows some more. But I've only made that mistake once, so. Another tool I used in a real case, I did a whole talk on this at LCA in 2020 called Fixing Windows Guests on Ceph, and a whole story on that. In that case, what was happening is Linux machines do all their I/O in 4 kilobyte blocks. Windows machines do it in 512 byte blocks. Most modern storage devices like all their I/O to be done in 512 byte blocks, sorry, in 4 kilobyte blocks, not 512 byte blocks. And what was happening was Windows was sending a 512 byte write, and internally Ceph was sending that to the kernel as a buffered I/O request. And the kernel only got 512 bytes, but it needed 4 kilobytes because it can't send any less than that back to the disk. So in line, when it made the right call to the kernel, that you expected the kernel to buffer in memory, it wasn't even going to wait to send it to the disk normally. It would then have to go out to the disk, read the rest of the 4 kilobytes, pull that in, change only that 512 bytes, and then go back to the program. It's called a read, modify, write penalty. And we didn't realize that was happening at the time, but what I did with this program was I'd already narrowed down that the pwrite v system call was taking a long time, and I didn't know why. So I then went and broke down with this program the latency of each pwrite vcall and by which process did it. And so from that I determined that the TP fstore op process, which is like an internal Ceph thread, I found that it had these bad latencies, and that was the process that I was interested in. I had another case. It was a murder mystery. There was something was randomly killing processes on the system, and I didn't know what, and that's a really hard problem to debug. Traditionally, there's no super easy way to find out who killed what. And so in this case, I attached onto every time we generate a signal in the kernel, I would print out which process sent which signal to which other process. And from that, I was able to figure out it was actually systemd killing my process for a very complicated reason to do with session scope management. But that's another excellent bpftrace example I had. And this is kind of a fun one that I like. All that stuff before was kind of looking at kernel stuff. This is using uprobes. And so what we're doing here is we're probing the SSL library, and again on the entire system, and we're hooking into the SSL read and the SSL write call. And when those are called, we actually read the buffer that was passed into SSL read and write, and we actually print out the data that the program is sending. If you've ever tried to debug like a HTTPS connection and you use TCP dump, all you get is the encrypted data. And sometimes you can convince your program to like write the encryption key out to try and decrypt that, but we can just bypass all of that, hook into the SSL calls and look at the unencrypted data before it's encrypted or after it's decrypted. This does unfortunately highlight a current limitation of bpftrace, which is that we can only print or capture strings up to 200 bytes in length at most. That is a fixable limitation, but no one's fixed it yet. And so there is some software, one's called eCapture, which uses like Python and Go to do this and can bypass that limitation and print out all the data. But if you use bpftrace to do this, you'll only get 200 bytes at a time. And as a bonus, because I wanted to throw an extra one in, a number 6 out of 5, I wanted to trace something in the kernel, but then correlate that with the kernel stack. And in this case, I was trying to understand systemd was at some point changing the CPU set of a process. That's a list of CPUs it can run on. And I didn't know why or from which kind of area of systemd was doing that. So you can actually wildcard kprobe, and unfortunately it's not on the slide right now, but I said CPU set star, probe every CPU set function in the kernel, and then print me out the user space stack of what ultimately called it. And so I could see all the code paths in systemd that were calling into those functions, and that let me try to figure out where to go looking for why it was changing the CPU set in a way that I didn't expect. So ultimately, there are many different methods of doing these things. Some of the limitations I talked about, like top, missing things, you can solve those in different ways. But the nice thing about bpftrace is it lets you solve a lot of those problems in a language that's very kind of sysadmin friendly. You don't need to be a kernel engineer necessarily sometimes. And always using the same tool rather than like there is a version of top called atop, which uses process accounting to kind of not miss processes, but it's very complicated. So it kind of lets you solve lots of problems in a quick and easy way. But there are a bunch of limitations, like that string length one, and so if you want to do kind of more advanced stuff, you can still use this same technology, but in a real language like Python or Go, and that gives you some more flexibility. There are a couple other related tools I often use for this. The perf tool itself, if you don't want to get into bpftrace, you can kind of do a lot with just perf itself. It just doesn't do that summarizing part for you. And FlameGraph, if you've never heard of, is a really great tool to show you graphically where you're spending CPU time, which can kind of help in these. And last of all, as a quick note, this concept of putting these little tiny event-driven programs into the kernel that are user-defined has kind of taken off, which some of you may or may not have seen. But now we're not just doing packet captures or tracing. You can now put entire network load balancers in the kernel, custom CPU schedulers, firewall processing, profiling, auditing. It's become like an industry. So the term BPF has become a technology, and every company that's doing crazy stuff, often in Kubernetes, is now putting all sorts of crazy stuff in it. And so if that sounds interesting or horrifying, I'd recommend reading up on it and seeing what you can do. If you want to find out more, there's some resources here. There's a couple good books by Brendan Gregg. He's a very, very good resource on this topic. That's where to find bpftrace. And if you YouTube bpftrace, there are a lot more talks that will go into a lot more depth. And that is all I have. So I believe we have, maybe not a couple minutes for questions?
A couple of minutes, a little bit of time. Anyone got any questions? My go-to tool for this is SystemTap. How does bpftrace and SystemTap compare?
That's a great question. So the question is, how does SystemTap compare to bpftrace? So SystemTap lets you do a bunch of the same things that bpftrace does, and has also done that for a long time. The way SystemTap worked internally is it would take a similar kind of language, it's different, but kind of similar. It would then turn it into C and compile it and load it as a kernel module. And so it didn't have that same kind of like, I mean, it tried to do its own safety guarantees, but it didn't have that same implicit safety guarantee of the generic BPF system. It also required you to compile a kernel, load a module, and that has become more of a problem now with secure boot, because you need to then sign that module and that kind of thing, which you kind of avoid potentially with the BPF method. But you can solve a lot of the same problems with SystemTap. Something I didn't talk about very much was right now when you probe a user space program, there's actually a much bigger performance penalty than the kernel side, because it does actually trap to the kernel and back every time one of those is hit. SystemTap had a solution for that where it would kind of push some of that stuff into user space. The same thing could be done with bpftrace, but no one's really done the work to make that happen yet. So there might be an advantage there in some cases.
Okay, thank you very much, Trent, for your time and effort. It's a little gift from us to you.
Thank you very much.
For your time. Just a little thing, people, the key card for the Oaks accommodation hasn't been claimed. So if you're staying at one of the Oaks venues, please check that you've got your key card, because finding out when you get there this evening is not going to be a lot of fun. All right, off you go.